So before we get into trying to find a derivative of something like that folium of Descartes from the previous video, what we would do is that we have to show how we use a method called implicit differentiation right here. So we want to try and find a derivative. So right here, I've actually got this linear equation written in a very nice well, it's in an implicit form, right? X's and Y's all mixed together on one side. Now we could isolate Y very easily, and we will just to compare in this example. But for right now, let me show you what the method looks like. Basically, what we're going to do is we're going to take the derivative on both sides with respect to x. And you think to yourself, well, what does that mean? It means that on the left-hand side, I treat that entire expression as though just it's some function that contains x, y's, whatever I've got over there, and I'm going to take the derivative of all of that with respect to x. And on the right, I'm going to take my derivative also with respect to x. So I have a derivative on the left and a derivative on the right, all in terms of x. So if I take my derivative, well, we actually kind of know what's going to happen in some ways, because if we take the derivative with respect to x of the first term, so the derivative with respect to x of 2x, we know is going to give us just 2 times 1. And we're going to then try and take the derivative with respect to x of 13y, and I'll explain that one in just a moment. And then we're going to take the derivative with respect to x of 15. Well, we know what happens when you take the derivative with respect to x of a constant. We get 0. So we're going to get, well, 0 over here. So the question is, what do we do? Well, this is, let's take this constant out, right? 13 will be multiplied by the derivative with respect to x of just plain old y. Well, in fact, we can just say, well, if y is implied to be some function of x, then whenever we take its derivative directly, we actually have 2 minus 13 times dy dx equals 0. So you're saying, well, okay, then what do I do with that? Well, dy dx, our whole goal then is to isolate dy dx. So what we might do right here is we say, well, okay, if I were to algebraically do it, I would have to subtract 2 from both sides, and I'd say negative 13 times dy dx, which was our derivative of y with respect to x, would equal negative 2, 0 minus 2. And then we could divide both sides by negative 13. And lo and behold, we get dy dx isolated as the fraction 2/13. Now, okay, I mean, dy dx is 2/13. It kind of makes sense, but let's look back at this, right? One way that we could have handled this is that this is a function that we could rewrite explicitly by isolating y before we start taking a derivative. And if I did that here, look what's going to happen. I'm going to take 2x, I'm going to subtract it from both sides, so I'm going to end up with 13y, negative 13y, would equal negative 2x plus 15. Then I would divide both sides by negative 13 and simplify my result, and I actually end up with this equation: y is equal to 2/13 x minus 15 over 13, whatever that ends up being as a decimal. Doesn't really matter though, because if we were doing this using the explicit function method, we would say, well, dy dx is the derivative of 2/13 x with respect to x minus the derivative with respect to x of 15/13. Well, 15 over 13 is just that's just a constant, so that's going to go to 0. But when we take the derivative with respect to x of 2/13 times x, as we showed before, we're going to end up with the constant times 1. That is to say, dy dx is equal to 2/13. And now it kind of makes sense because, whoa, that's the slope of this line. And we got the same thing by just taking the derivative of everything exactly where it's at. So this over here on the left, this is the implicit differentiation method. We take the derivative on both sides equally with respect to x. Anywhere we run into y, we isolate it to get dy dx, and then finally we do the algebraic isolation of dy dx to one side. More to come.